sound. I can lift you up. I can show you what you want to see and take you where you want to be. You could be my love. Even if the sky is falling down, I know that we'll be safe and sound. We're safe and sound. We're safe and sound. We're safe and sound. We're safe and sound.
So I took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 60,000 components on a chip.
First thing you have to tell him is,
Yeah.
guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
All right, so today we are going to talk about the topic of virtual memory, right? But I hope everyone is safe and sound as what we played before the lecture. And, like I've been living in tropical zone for more than 20 years. And I know for the location of San Diego, it's not going to have any huge hit on because of this kind of very weak tropic storm. And probably because also the hurricane is named Hillary. If it's named as like Trump, I would be probably worried a little bit more. But well, I hope everyone is doing well. However, right? One thing that changes my mind is actually yesterday, UC San Diego sent out a letter saying that okay, it's up to the advisor to decide if you want to hold the lecture in person or not. And when the school says that, it implies that, okay, I mean, you can do in person, but no matter what happened, it's not our responsibility. So once the school say that, okay, you know what they are implying to, right? So sometimes I feel pretty sad, like being an adult and a young profession, you learn a lot, like hearing the words behind the words. And so for this one, it actually means that school encourage you to hold a lecture remotely, even though you think it's safe. So that's why we have the lecture remote today, and I hope you will still enjoy it. But before we start, it's always a good idea for us to remind ourselves where we are coming from. So if you remember the pieces of code that we had demoed in the last time, which if we change the dimension to like 7,000K, 70K, right? It means that we are going to consume more than 32 gigabytes of memory, which is more than the amount of memory that we have on our cluster. But later on, as you see, right, even that's the case, we are still fine. And a lot of you who this is the demo I have, right? So if we make it super large, the code will still run. You will still see the average, and everything is still fine, right? And the reason a lot of you mentioned is because we have the virtual memory abstraction. And same thing for here, right? So the first thing that you know is that with virtual memory abstraction, it's actually helping us to accommodate programs that needs large memory. And even though you think, well, I have a small program, why do I need virtual memory, right? Then another incentive here is, well, look at this demo. We have multiple instances of diskette, right? And with virtual memory abstraction, even though everyone have the same memory address, because when you compile the code, right, one thing you learn about the compilation is that the compiler will decide the memory address of global variables. So once you compile the code, the memory address of global variables are already fixed. However, different instances should have different values of these global variables internally. So with virtual memory abstraction, we can have the isolation from one process to another. So each of the running program would be a separate identity without under the fear that their values will be affected. So those are the good things about virtual memory abstraction, right? So that's why we need virtual memories. And the idea of virtual memory is pretty much like this, right? So even though I have two programs, two program instances from the central program, right? Even though different programs, they have the same memory address like this one being used. However, in process A, I will look at different, up this address from my virtual memory address space. And for process B, I will look up this address from my virtual memory address space, and then they will be interpreted as different things. So that's how the virtual memory abstraction helps to maintain the isolation and etc., etc. So that's where we are coming from. And today we are going to continue our discussion on that virtual memory abstraction and how architecture-wise would support virtual memory. So first of all, right, here's the concept of virtual memory. So the concept of virtual memory is that your system provides an abstraction that each application can freely use an address space that starts from 0 to the very end of the address space. So typically, when we say like 64-bit memory address space, it means that your topmost memory address that an application can use is 2 to the 64 minus 1 if you start with 0. And that abstraction exists in each application. So you can imagine, regardless, unrelated to how many memory modules you install in the system, every program can freely enjoy this virtual memory space. And this is architecture independent. Once you have, well, processor independent or machine independent, it's instruction set architecture related. So in modern x86-64 architecture, we plan that we support 64-bit memory addresses, but in fact, modern processors like Intel or AMD, they think people won't use that much. So they support 2 to the 48 minus 1, but that's in real practice. But today we are simplifying our discussion. So we assume 64-bit address space can support up to 2 to the 64 minus 1. However, okay, so everyone would virtually have this amount of memory. But now your question is, okay, but I don't physically have that many memory installed, right? So how virtual memory abstraction will handle this? So first of all, right, they use a mechanism called demand paging, right? So whenever an address is referenced, so in the very beginning, I put nothing in the memory. Although in von Neumann architecture, we mentioned to run a program, you need to have everything presented in the memory before you can start a program. But in virtual memory abstraction, we make this claim, we slightly alter this claim in a way that as long as everything is presented at the level of virtual memory, we are allowed to start executing the program. However, so when we really want to execute the program, remember, we still need those instructions and data. So we load this content on demand. So for example, if every program by default, they would have a starting address in an operating system. And it's probably not too difficult to guess that, well, when you want to start, there is an agreement between your operating system and the hardware saying that, okay, load this program and the program should start at this address. So for example, now I'm starting a new program and it start the very first instruction, and that's currently say this instruction address should always be 0, right? So if I want to fetch the instruction from the very beginning of the program, it should be located at 0, and that's where you are going to load your program into that virtual memory address space. So when that address is referenced, remember, currently there's nothing in the physical memory. So once that address is referenced, someone in your system is responsible for having that part of instruction presented in the physical memory as what we draw here. So right now in modern systems, typically your operating system is responsible for that. So what will happen is that when the CPU wants to access a data or instruction, and when it's not in the physical memory, right, it will trigger the operating system to say, hey, can you figure out where is it in a virtual memory abstraction and load it into the physical memory location. So what will happen is that, well, the operating system will load a chunk of data or instructions that contains the demanding one into the physical memory. And once we are done with that, your program can continue execution until it needs something, but that something is not in the memory. So for example, if right now you want to access data and the data is currently not in the memory, then again, the same process will come up. We load the stuff that you want into the memory. And similarly, you are allowed to run another program concurrently, right? And even though it's instruction 0, but through this process, we are going to load instruction 0 into different locations in a physical memory. So even though both of them, like both of them seem to be the same content, but they will physically occupy different locations, right? Or even though they are having the same address, as long as they are coming from different programs, they should be occupying different physical locations in a memory system. And again, if you are accessing data, we will load the data dynamically as you need it from the virtual memory abstraction to your physical memory. Okay, so in this way, right, you have a feeling about virtual memory in the following ways. So first of all, virtual memory is an abstraction of memory space available for programs and software programmers. And the reason why we say it's an abstraction, because when you have 64-bit virtual memory address space, it doesn't necessarily mean that you need to have 2 to the 64-bit, 2 to the 64 byte of memory installed, right? You don't basically need that. So it's an abstraction. And program is queued using virtual memory addresses, right? Because everyone is on top of that abstraction. So everyone should be unaware of what the underlying machine architecture is or underlying memory implementation is. So one thing that you should remember is that, okay, why everyone, like every forked program in the previous program example, they all have the same memory address, but they never overlapping because they are all using virtual memory addresses instead of physical memory addresses. Okay, and who handles this virtual memory address and physical memory address mapping is actually a collaboration between your operating system and hardware. And by hardware, it's typically your memory subsystem and your processor to handle this mapping. And previously we mentioned, right, whenever we need something, we will load something from the virtual memory abstraction into your physical memory location. And as we previously learned, if you have to load everything one by one, it will be terribly slow. So one concept that is similar with the cache is that we organize memory locations into pages. So pages, they are effectively consecutive chunk of data. And every time when you need to have something presented in the main memory, it's by page. So in this way, right, you can imagine, okay, even though I'm just loading like one bit of data, what would happen is that I would load the whole content. I would load the whole content of the page into the main memory, right? Pretty much, right? If you remember this figure, right, you will figure out, it's pretty similar to something I learned before, right? That's the cache. So here's the thing, right? There are a lot of analogies that you can start to feel between the virtual memory address, the virtual memory abstraction, and the cache is that virtual memory, the basic granularity of loading data from the main memory, from the virtual memory to main memory is a page. So page is the very basic unit. And you can consider the main memory now is pretty much like a cache of your virtual memory content, right? So in this way, you start to figure out, okay, why things have to be done in a page perspective so that we can exploit the spatial locality of virtual memory access, right? However, because main memory latency is longer, so every time we load more data into main memory, right? So those are the things, right? And for cache, right, we logically partition the memory space into blocks, right? So you can see there are lots of similarities here, right? And as we previously mentioned, why we want virtual memory? Because there are lots of benefits of having virtual memory, right? First of all, you don't need to worry about how big your physical memory is installed. And the other thing is that you have multiple applications and they can all run concurrently without interfacing any issues with that. And the mechanism that we are using nowadays is called demand paging. And with demand paging, it's pretty much like treating your physical main memory as a cache of your virtual memory. And because it's a cache, so there are a lot of similarities there. So for example, right, every time when we load data into the cache, it must be block by block. And in virtual memory abstraction, every time we want to load something into the main memory, it must be page by page. And you must remember that in the cache architecture, we spend a lot of time to figure out if the block exists in the cache or not. And same thing, you have to figure out if the page exists in the virtual memory or not. And that thing is page table in a virtual memory abstraction. However, one thing that is different, or say still the same, but we rarely do this in cache abstraction, is in virtual memory abstraction, typically we will allow a virtual page to go anywhere in a physical main memory. So in this way, you can pretty much consider the main memory as a fully associated cache, fully associativity cache of your virtual memory. So with that, right, C equal to ADS will still apply, and we will see that. And another thing that is also similar, right, is that, okay, so now you guys see that, okay, if I have a physical memory that only allows 4 pages concurrently, what happened, right, saying that if process Chrome needs more memory, then what will happen is that, okay, my virtual memory abstraction will figure out who in a physical memory should I kick out. And if I figure out I should kick out this light blue guy, right, then what will happen is that, okay, again, if I need to write back. If I can directly kick out, I will kick out, right? And then once you have done that, that's when you can fetch the new content in there, right? And you might wonder, like, where am I picking out stuff to? And that's actually your persistent storage, or say your disk, right? So you can consider disk now as an extension of your memory hierarchy, and that's where we maintain everything for the virtual memory abstraction. And the operation of writing back stuff and getting the new stuff in is called swap. So right now, most of the virtual memory system implementation has this two feature. One is demand paging, and the second part is the swapping. Regarding how to implement swapping and what's the policy of swapping, that's the scope of CSE120, and in this class, we are not going to dig into that much detail. And if you are still interested about that, and please review your operating system book, or take CSE140 in the future. But for now, as computer architecture class, what we want to talk about is the address translation. So as we said, right, if all your programs are running inside the virtual memory abstraction, it becomes essential for your processor to translate virtual memory address into physical memory addresses every time when you need to access memory. And remember, when we want to fetch an instruction, instruction comes from physical memory. When we need to access data, data comes from physical memory. So it's very important that we can have a mechanism that helps us to translate those addresses in a very efficient way. But before we talk about that, let's look at how conventional, or say very naive way of handling this address translation. So first of all, right, we mentioned the whole virtual memory abstraction is pretty much like a cache. So if it's a cache, right, C equal to ABS. And also remember, right, so this is a fully associativity cache. So the S is equal to 1. So it's effectively C equal to AB, right? And what does that mean? So, and we also mentioned that the page size is pretty much like a block size. So saying that if today I have a system with 4 KB page size, it means that it's pretty much C equal to A times, 2 to the 12, right? And this is the B, right? And remember, when we are doing the cache access, we need to partition the address into the tag, index, and offset. And for this one, right, we know S is equal to 1 because it's a fully associativity cache, and log to 1 equal to 0. So there's no index bit, right? And we know log B is for your offset, right? So for log B, it will be 12 if you have 4K pages. So what does that mean is that, okay, so in the remaining, right, that will be your tag. So if I know my page size, you pretty much can know how do you partition your virtual address. So in this way, right, if I am assuming 4K page size, which is the most commonly used one in modern system implementation, I can pretty much partition my address like this. So if I have an address like0x000B, and I know for if my page offset is 12 bits as suggested, right, then this page offset, they would probably tell you, okay, the byte that you want is within which location within a page. And the remaining is considered as something like a tag. And in the virtual memory abstraction terminology, this is called virtual page number. And what we are going to do, right, like what we did in cache, is that we use the virtual page number to see if there is a match of physical address in our system. So, and in cache, we have a hardware called tag array to deal with that. However, in virtual memory abstraction, because it's a software-based abstraction, so we don't actually have a hardware for it by default. What we really have is some kind of software data structure called page table. So this software data structure called page table, the location is actually agreed by both the operating system and the hardware. So when you launch a process, if your operating system and your software, your operating system and your processor will have an agreement. Okay, this is where you should put your page table, and then they will program that location to store the page table. And regarding the format of the page table, they also have an agreement. So, okay, with that agreement, the hardware would parse the requesting virtual address and use the virtual page number to see, okay, is there a mapping in this table, right? And if there is a mapping, right, then they can directly output that mapping to know where the physical location is. And that's how you get the translation. And if there is a translation, it means that, okay, the data that I'm requesting is indeed in a memory, pretty much similar to what you have learned in a cache. Okay, so that's the concept of basic implementation of page table. So now I have a question for you. So if I have a 64-bit virtual address, each page is 4 kilobytes. And each page table entry is 8 bytes because you have 64-bit addresses. What magnitude in size is the page table for each process? All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after the first round, okay, we have a pretty diverse discussion on the answer. So let me see if I can wait, how to enable the breakout rooms. So okay, so let's try to put you guys in 2 breakout rooms and let's see what you guys have after the discussion. So again, we have, okay, so one thing that I want to mention. So one limitation with the breakout discussion for Zoom is that you won't be able to see the screen after you enter the breakout room. So what I would suggest is that right now, take a screenshot and so that you have an idea about what the problem is about. And now take a screenshot right now, okay? And then let's go to the breakout room. All right, has everyone voted again? Okay. All right, let's try to see what you guys think after the discussion. Okay, so after discussion, okay, we see some slight changes. More of you think it's D, right? So how do you guys solve this? Can some of you share your experience with us? Like, how do you end up finding the answer? Hello?
Um, so I don't think I got the right answer, actually. I'm not sure, but
Okay, but
I
never
can
mind, right? Like, that's why we want to learn.
totally. So I guess I wasn't 100% sure if each page needs to fit in a page table or each page table needs to fit in one page or not. But I guess my other approach would be, well, so we know 64-bit address space. We have 2 to the 64 minus 1 total
Mhm.
potential
So you
entries.
have so okay, you have this many
Entries,
entries, okay?
and they're 8 bytes each. And
They
if
are
you
8 bytes each.
um
Okay,
and
so
yeah,
maybe we can go back and look at this one, right? So the page table is translating what? Brendan, are you there yet?
yeah,
Translates. Oh, sorry about that.
the virtual address is the index into the page table, which maps to the physical address. In
Are we taking the whole virtual address?
no, just part of it, not the offset.
Right. So how many of this do we have? How many distinct virtual
I see,
page number are we going to have?
I see 2 to the 50 minus
2 to the what?
50 minus 1, right? Because we have 12 bits for the offset.
But then we also start with 0, right? We also start with 0, right?
Mhm.
So you have a complete 2 to the 64 bytes that you need to address, right? And each of the page is 4 kilobytes, right? So that's the total number of entries you need in the page table. Agree?
Yes,
Are you okay with that?
yes.
Okay. And because each entry is 8 bytes, right? So the size of page table is essentially 2 to the 55 bytes is equal to 32 petabytes. That's just for one process. Okay, so did you guys hear the big issue that we are hitting into with the virtual memory abstraction right now? What was that? What's the big issue of the virtual memory abstraction?
Page tables are way too big.
You got it, right? So the page table is this big, right? How many of you have 32 petabyte of memory, right? None of us have that, right? And even though I have 32 petabyte of memory, can you imagine the whole physical memory is only used for page table storage? That doesn't make sense, right? So that's not going to work, right? So conventional page table has a big issue, right? It's very huge, right? It's too huge in a way that we cannot put them in the memory, right? And the other thing is that, well, if you look at the way how we manage the page table, it's consecutive, right? So you also have to spare a huge amount of consecutive space within your virtual memory address space to just for the page table. So both are impossible. Both are impossible, right? So that doesn't make sense. All right. So two things we have to address. First, do we really need a large table? Do we really need a large table? And the answer is probably not. So let's see how your program typically would use virtual memory address space. So first of all, when you load your program or start running your program, in your virtual memory address, typically from the beginning, the very beginning, you are going to place your text session, which contains your instructions or say your code. And after the text section, there will be data section, which stores your global variable. So if, for example, if I have a global variable A, B, C, they belong to the static area, which I have here. And if you have instructions that are compiled, they would be put into the code section or text section in your compiled code. And once you have done that, you can start running your program. And within the rest of virtual memory, we have two different ways of using them. The first way of using the remaining section of the virtual memory is called heap. And the other one is called stack. And here's how we are going to use them. So when you call functions malloc, calloc, or any dynamic allocated data that is visible throughout the whole program, then it grows from the heap area, which its beginning address is the end of your static data section. And gradually you grow the heap allocate. So the malloc function will pretty much find out, okay, what's the last allocated address from the heap area, and gradually use data in this direction if it's allocated by functions like malloc, calloc. And if you are calling a function, like you want to put arguments, or if you want to allocate local variables, they comes from the stack, which is starting at the end of your virtual memory address space. So for example, if your virtual memory address space with the last location as 2 to the 64 minus 1, the very first local variable would have addresses ending at this location. So you can imagine, here's how you are going to use your memory address. You gradually use stuff from the beginning of the heap, as well as gradually use stuff from the end of the stack. However, in the middle ground, which is this big area in your address space, you probably would never use them, right? So that's the reality of memory usage. So you can imagine this is something is going to be so if you can structure your page table in a way to avoid allocating entries for the middle section, that's how we can make the table smaller. And the other thing which we want to address is that we don't want a giant consecutive page table. So our thought is that, okay, remember, in a hardware, we actually store data in page-based. So can we break up all the page table entries into pages instead of storing them in a giant segment? So if you think about each page table entry in 64-bit is 2 to the 3. And as we mentioned, right, each page is sized as 2 to the 12 bytes in modern implementations. Then you can think about, okay, for each page table, I could break up them into pages, and each pages can be considered as a node that contains 2 to the 9 page table entries. Okay, so one good thing about consecutive page table is you will be able to know the index easily because it's sequentially increased. However, if its page is broken up, you know their location is pretty random, right? So what would and okay, so sorry about this. And okay, so when we break up them into page table, right? One good thing is that naturally you only allocate a page table entry nodes on demand in a way that, okay, if I start to reference the code, if a translation has been established, that's the time when I allocate a page table entry nodes. However, if so, however, for the middle section that we never mentioned because we don't create those page table entries since there's no demand, then we probably won't create any nodes for them. That's how we save the space. However, a big question here is that because these nodes, they are spread out, so we really need a mechanism to locate them in the memory. So what we end up with is that we built a B tree structure for us to easily locate those page table nodes. So the mechanism is that we start to build hierarchical page table in a way that, okay, whenever I need to create page table nodes, I allocate a page. But in the meantime, to index this page table nodes, I also have to create B tree nodes that help me to navigate to the end location. And the thing is, because each page can store only up to 512 pointers to 64-bit address. So it turns out what would happen is that it's a B tree which each node has 512 entries pointing to their next level page table node. And gradually, when you traverse, you will be able to find the last level page table node in this hierarchical page table. And in this way, you can avoid the consecutive data structure. You can also condense the size of your page table. So that's where we are end up with. I know everything seems to be very, very complicated. So let me just show you an example how x86 do this today. So as we previously mentioned, x86, although they claim to be 64 bits, however, it's a biggest lie. They only support 48 bits of data. And for the 63 to 48 bit, it's all ones. So you can ignore this part. In fact, x86 only have 48 bits of virtual memory address. And once we receive that 48 bit of address, we partition the address into 5 different segments. Within these 5 segments, one part is the page offset, and the rest 4 are considered as indexes for you to look up for a translation. And as we previously mentioned, because each page table node can only store up to 512 entries, so that's why you have 9 bits in each level of index. So what would happen is that I take the very first, okay, so one more thing. In x86 processor, as we mentioned, the operating system and the processor has an agreement where should you store your page table. And that address is actually programmed in a spatial register in x86 processor. So whenever you need to translate your address, the x86 processor will look up that register and see, okay, where is the root node of that hierarchical page table, which is essentially a B tree in a system. And that root location would actually contain a page table node, which contains 512 entries. And based on the 9 bits we have in the most significant 9 bits of your memory address, we would use that address as the index to access that table. And with that table node, it will give you a pointer to the next label page table node that will contain another layer of translation of your memory address. And what will happen is that we will continuously use the second most significant 9 bits as the index to access the next label, which would point us to the next location in the page table node. And then we use the third most significant 9 bits in the index to get the next table node. And finally, we use the last label index, which is also 9 bit, to figure out where in your page table entry should I look for the data. And the last label index would actually give you the physical page number. And again, concatenated with the page offset. That's how you would be able to get the complete virtual memory address. So that's the whole process. Okay. So now after going through this process, I want to ask you one thing. According to our current discussion, and assume the page table, because it's so large, we wouldn't consider it would be part of the cache. So if everything is in a memory, so how many memory accesses can a move instruction that also need to access data memory incur? All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after the initial vote, we see B and C, they are probably popular answers. So I already sent out the screenshot of the question through the chat. So what I would encourage you to do right now is to open a screenshot so that you know what question we are discussing. And now I'm going to put you guys into the breakout room for discussion. So now go ahead and discuss. All right, let's wrap up in 15 seconds. All right, 5, 4, 3, 2, 1. Time is up. Okay, so let's see. After discussion, more of you leaning toward B instead of C. Some of you leaning toward D now. So, can someone share your thoughts with us? Like, what do you guys think? What do you guys think? So some of you think it's B, C, D.
So I could go ahead, I guess, just say my
Sure.
thinking. So my thought is, okay, we first go to that special register that points to the
Mhm,
root. Okay, so
mhm.
that's one access to get to the root. And then we
Okay,
have,
one access.
and then, so I'll see, see, according to this, it should be 5, isn't it? Which isn't on there. I put 6, because it's one for
Okay,
the
what's the
root,
other?
then
One for the
for each
root.
level, and then we have one at the end, because we actually have to access the data.
That's here, right?
Yeah,
1, 2, 3, 4, 5.
yeah.
Right, because register itself is not memory. But this is the move instruction, right? What does that mean?
Oh, are we gonna have to like reload it back in? Let me see.
It's a move instruction, right? So move instruction has data memory access, that I agree, right? But don't forget where the instruction is coming from. And how instruction address is encoded. Is it also in virtual memory? Right? So if you count that, it's actually 2 times 5 is equal to 10. Right? So you may have 10 memory accesses for just a move instruction, because 5 for instruction fetch and 5 for data access. Right? And you must already remember that each memory address access is really slow, right? It could be 50 cycles, right? So if you have 10 of this, you are spending 500 cycles in just getting the instruction and the data, which means that your program is very, very slow. And within this period of time, only 2 accesses are actually in data or instruction access. The other 4, they are pretty much for address translation. So address translation overhead is definitely something we need to avoid. So a very intuitive solution that you might have for now is that, okay, since every address needs to be translated, what I need is probably a cache for page table. And architecture-wise, we call that translation table, or cache of the translation table called translation look-aside buffer. It's pretty much a cheat sheet of your page table that cache frequently used page table entries. So what happened is the very naive design is once I load an address, I know it's a virtual address. So I look up the physical address and use that to access my cache. However, as you could imagine, because you have to perform this translation in between your processor and L1, and you have to do this every time when you access the cache. So it's making your every access slower, which we don't want. So another proposal is that, okay, the reason why we need to translate every address is because our cache is actually using physical address for its tag and index. So what if I use virtual memory as the tag and index? So what we think is that, okay, when I load a virtual address or store a virtual address, I use this address to translate, to fit into the TLB for translation. But in the meantime, I use that to access L1 cache. And whenever it's a miss, that's the time I would use the translated result. However, the big issue with this proposal is that, remember our demo, right? Many applications, they would have exactly the same virtual address, but they are physically different addresses. And even though for the same application, you could have an aliasing in virtual address in a way that you might potentially create multiple alias to several physical objects because your operating system or your language support that feature. So if you have both features included, then it means that you have the issue that you won't be able to tell the case where a single virtual address should be mapped to different locations or multiple virtual addresses to map to the same physical location. So this idea would not be working in real practice. However, it does teach us something is that if we can allow the key to allow parallel access between TLB and L1 is that you have to use virtual address. And so here is the solution that we came up. That's called virtually indexed physically tagged cache. And the reason why we designed this cache is, right? So the key thing is that if you remember what we have taught before, if you want to access cache blocks, if you want to know if it's a hit or miss, all you need is the index field in your cache. So the idea here is that, okay, if we use virtual memory address to access the cache, to index the cache, then we don't need a translation. But what if the tag field that I store in a cache is actually coming from the physical address? Then I can receive the same effect as using physical address to access the cache. So the idea of virtually indexed or physically tagged the cache is that, okay, so if I want to use the virtual address to access the cache, but also guarantee if it's the physical address to access the cache, they can map to the same set. So what end up is that, okay, you have to ensure your index field must be located within a region of your memory address that remains unchanged before and after translation. So as you guys can imagine, which area that remains the same after the translation is actually your page offset. Okay, so now the question is, if that's the case, right? What will happen is that you have to ensure that your index and offset must be within your page offset. And in this way, you can ensure no matter I'm using virtual address or physical address, they would pretty much locate me to the same set in my cache. Right. So the process is pretty much like this. And if your tag field stores and the other thing is that if your set index and block offset is equivalent to your page offset, the tag part of your physical address would pretty much be your physical page number. So in the meantime, when I perform the TLB lookup, its output is essentially the tag that I need to compare. So the process of accessing virtually indexed physically tagged cache was pretty much like this. So given an address, I will partition the address into index, offset, and virtual page number, which is the tag field in the cache as well. So this part remains the same. And don't forget, the set index and block offset, they are the same before and after translation. So no matter you are using virtual address or physical address to access the cache, they are effectively the same. You are going to go to the same set and use the same block offset. So in the meantime, I use the page number and to access the TLB. And the output will pretty much be the physical page number as well as the tag field in the cache. So in this way, if your cache is using physical address as the tag, then the output, if the output matches the text that you have here, it means it's a hit. So in this way, you are pretty much using physical address to access the cache effectively. So this is the idea how virtually indexed physically tagged cache work, is that you just make sure that your set index and block offset is part of your page offset in the virtual memory abstraction. And after you translate it, your physical page number would be equivalent to the cache tag in the physical memory address partition. So that's how you can effectively use virtual address to index the cache. But when you compare the tag, they are both on physical pages, so that you can avoid the confusion of the complicated virtual to physical memory address aliasing problem. Okay. However, designing such a virtually indexed physically tagged cache has some limitation. Remember our C equal to ABS formula. The number of block index, block offset and set index is log B plus log S. And your page offset is log 4K if that's your page size. So if you want to force your set index and block offset to be equivalent with your page offset, it means log B plus log S can only be 12. So use our C equal to ABS. If you have a direct map cache, your cache size can only be 4 kilobytes, which is very limited. So that's the biggest constraint about virtually indexed physically cache. So now I'm asking you a question. So if you want to build a 32 kilobyte virtually indexed physically tagged cache, what are the parameters should be set for B and A? All right, let's wrap up in 15 seconds. All right, so now I have sent out the screenshot, but in the meantime, okay, it looks like this is a question we really need a lot of discussion. So why don't you guys open that screenshot and let's discuss this question in breakout room. All right, let's try to wrap up in 5 seconds. 5, 4, 3, 2, 1. Okay, so after this discussion, I don't know if you guys really discussed, but here's what we found. So yeah, pretty diverse answer, right? So here's the thing. The limitation of virtually indexed physically text the cache is the constraint is log B plus log S must be within 12 if it's a 4 kilobyte page size, right? So what we need to do is that can we find a parameter with C equal to ABS that would allow the 32 kilobyte capacity to fulfill the requirement of log B plus log S equal to 12. So the answer is only D will fulfill that. And here's the math, right? So C equal to ABS is 32 kilobytes, so it's 32 times 2 to the K, 2 to the 10. And we don't know the A, we don't know the B, and we don't know the S. But we know log B plus log S must be 12. That's the limitation. So if you look at the first one, it's 32 byte blocks. So the B is 32, and if the A is two-way, right, then it's not going to work out, right? And because which means, so this is 2 times, times 5, so it will be 6. So this part is already 15, right? So that means that you need to have 2 to the 9 number of sets, which would make 2 to the 5, so 5 plus 9, that will be 14 instead of 12. However, if you look at this one, right, if you have 2 to the 6 bytes times 2 to the 3, and your capacity is 2 to the 15. So which means that the number of sets you have is 2 to the 6. So 6 plus 6, that will be 12. So that if you examine all the options, that's the only one that fulfill the demand of virtually indexed physically tagged cache. And if you don't trust all modern processors, when they design their L1 cache, they are pretty much limited by this. So for your for the processor we use in a lab, it's a 48 kilobyte 12-way cache. So if you look at that, right? So it's 2 to the 15 equal to 12-way. So 12-way is 3 times 2 to the 4, and 48 kilobyte is 3 times 2 to the let me see. So it's 2 to the 14, right? Because 48 is equal to 3 times 16, and kilobyte is 2 to the 10. So it's pretty much 2 to the 14. And if you have 12-way is 3 times 2 to the 2, and your block size in modern in modern Core i7, Core i3, they are all 2 to the 6. And with that, right, it's 14. So this 3 got canceled. This is 14, and 14 minus 2 minus 6. So you also got the number of sets as 6. So even with the 48 kilobyte cache we have in our processor, that also fulfill the demand of log D plus log S equal to 12. So if you look at, so some of you might question, okay, why can't we grow the L1 cache size a little bit further? Because to make the idea of virtually indexed physically tagged cache work, that's the limitation that we have to put on top of it, right? And there's no way we can avoid that. And as a result, that limits the L1 size overall. All right, so this will conclude our lecture today. And starting from tomorrow, well, as I can see, it's pretty sunny outside. So I believe starting from tomorrow, we will be back in person. And so we also have a midterm in person tomorrow, and it's going to be 2 p.m. to 3:20 p.m. There's no exceptions for that. And there is already a midterm review lecture that's already online since last weekend, but I don't see a lot of you looking over it. So please make sure that you watch it before you take the midterm. And the sample midterm slides are already released with the last lecture, not this one. And some of you were asking about solution, but in fact, all the questions are already presented before in the lecture. So the reason why I don't provide solution is because I really want you to go back and look over those slides. And for the in-person exam, it's a closed book, closed notebook, no cheat sheet allowed. And some of you were arguing that, oh, online exam is not fair, it's longer compared to in-person ones. And the reality is that scientific research already showed that the average American can type 40 words per minute, but can only handwrite 13 words per minute. So you already got 3 times advantage in typing speed. So having the exam question 1.5 times is actually not fair to in-person students because they are supposed to be 3 times rather than 1.5 times. Some of you might be arguing that you are not familiar with LaTeX equation. However, LaTeX equation, you can consider it's part of the requirement of the course. Some of the course want you to learn Python, but have you ever complained about that? So don't complain about learning new things, but also not familiar with the new things, because that's part of the requirement. And it's also becoming a standard in Microsoft Office equation editor and Mac. And For the online one, it's an open book, open note test. So if you are really not confident about your skills of mastering those LaTeX equations, I mean, there aren't that many formulas you need to know for this class. And you can definitely pre-type some of the equation and just replace them with numbers when necessary. So again, it's online exam, but doesn't mean that you can cheat. So anything that you think might be cheating, you shouldn't do it. Other than that, enjoy the rest of the day, and I will see many of you tomorrow. Okay, Brandon, question.
So small administrative kind of question. For the next, are we gonna have the next assignment assigned on Tuesday as well, or is that gonna be pushed back a little bit?
So the due date will still be on Sunday, and it will be released on Tuesday as well, because it's going to be, I mean, we still have virtual memory lectures, right? So, and also typically the assignment should also cover the material of the whole week, because if it's due on Sunday, it's supposed to be something that covers the whole week.
Thank you.
Okay. Any other question? All right. If not, for people in person, I will see you tomorrow. For people online, don't forget to open Gradescope on time tomorrow. Other than that, enjoy the rest of your day. Hopefully, everyone will be safe and sound.
Professor.